Yeah, going ahead in this. So we would like to put forward this relation. This relation is basically the relation for the current in a diode. We don't have this derivation. I picked it up from an electronics book of higher standards. But this formula will tell us something about this particular graph. So this is here stands for this current which you can see here in the reverse direction, which is constant. It has a very special name. It is called as the reverse saturation current. The drift current which is going to flow in your diode when it is reverse bias, it is called as the reverse saturation current. And the reason for calling it as a reverse saturation current is, first of all, it's a reverse current, and second is that it's constant in magnitude, and that is why this word saturation is used out here. So this is here stands for the reverse saturation current. E raised to q, where q is the charge of the electron, v is the potential which you're applying, that is the forward bias or the reverse bias. K is your Boltzmann's constant, T is the room temperature, -1. Okay. Now you can see here that if your forward bias, if you don't give anything, V equal to 0, then E raised to 0 ho jayega, and that is 1. So your I is going to be therefore Is into, this particular value, that is 1, minus Is, and that is equal to 0. And that's how what you see here. So this particular point, what you see here, the current is 0 when your applied voltage is 0. And because you have an exponential term out here for very small values of voltage, okay, so for very small values of voltage, soon you will start observing an exponential trend. And that's what I just wanted to write this equation for. That's all. So this curve here is an exponential curve. That's all we need to know, and that is coming from this equation, जिसका derivation हमारे syllabus में नहीं है. So we don't have to memorize this and all. It's just for understanding why this curve became exponential in nature. Now, this threshold voltage which I've written here is actually different for the germanium diode and the silicon diode. You can see here that this PVI characteristic that has been plotted is for a silicon diode, where this voltage is 0.7 volt, approximately 0.6 to 0.7 volt. And this voltage we call as the threshold voltage, or it's called as the cut-in voltage. So cut-in voltage is of the order of 0.6 volt for a silicon diode. But the same threshold voltage happens to be around 0.2 volt for a germanium diode. And the reason for that, partly you can see from this equation, that is the reason why I wrote this equation also, that the current is equal to Is, where Is is the reverse saturation current. Now, if you compare the germanium device and the silicon device, which device has a smaller energy band gap? ये जो smaller energy band gap है between your valence band and conduction band, is that for germanium or is it for silicon? ये कौन सा है और ये कौन सा है? So first diagram is of germanium or silicon? Anyone remembers the values which I gave in the last class? Germanium, correct. Because germanium has an energy band gap of how much? Anyone remembers the value? ये सब याद रखना है. हाँ, 0.7 इलेक्ट्रॉन वोल्ट. और इसका कितना है? सिलिकॉन का बैंड गैप इन टर्म्स ऑफ इलेक्ट्रॉन वोल्ट 1.1 इलेक्ट्रॉन वोल्ट, करेक्ट, 1.1 इलेक्ट्रॉन वोल्ट। सो अगर एनर्जी बैंड गैप अगर कम है, then what will happen to the number of minority carriers? माइनॉरिटी कैरियर्स किसमें ज्यादा रहेंगे, जर्मेनियम में या सिलिकॉन में? माइनॉरिटी कैरियर्स नंबर इसमें ज्यादा या इसमें ज्यादा? How will you take a decision? Minority carriers are formed due to what? What reason? Due to thermal generation. तो थर्मल जनरेशन में यहां पे ज्यादा जनरेट होगा कि यहां पे ज्यादा जनरेट होगा? जर्मेनियम में ज्यादा रहेंगे, करेक्ट। So germanium में there will be more because whenever a thermal generation happens, the electron has to get sufficient energy to cross the band gap. और यहाँ पे अगर कम value है तो they can easily cross over. So minority carriers are going to be more. And if minority carriers are going to be more, then what comment do you have about the reverse saturation current? किसका reverse saturation current ज्यादा होगा? जर्मेनियम का reverse saturation current सिलिकॉन से ज्यादा रहेगा या उल्टा लेस देन रहेगा, ये दोनों इक्वल रहेगा? इनमें से कौन सा करेक्ट है? रिवर्स सैचुरेशन करंट ऑफ जर्मेनियम इक्वल, ग्रेटर, लेस? greater, that's okay, greater. Why greater? Because more number of minority carriers, and more number of minority carriers in the reverse in the reverse biasing case, the minority carriers are the ones which are drifting. So the value of the reverse saturation current is much higher in germanium as compared to silicon, and that's one reason what you see here also, the reverse saturation current is sitting out here. So you can see that जिसका रिवर्स सैचुरेशन करंट ज्यादा है वो जल्दी ऊपर निकल जाएगा, तो ये आपका जर्मेनियम का यहां पे रहेगा और ये सिलिकॉन का ऐसा दिखेगा, करेक्ट। सो जर्मेनियम का एकदम फास्ट पिकअप हो जाएगा करंट, बिकॉज इसका रिवर्स सैचुरेशन करंट ज्यादा है ना। तो दैट इज द रीजन व्हाई जर्मेनियम का जो वीआई कैरेक्टरिस्टिक है वो ऐसा दिखता है, और इसका जो थ्रेशोल्ड वोल्टेज है ये 0.6 वोल्ट है या 0.7 बोलो, और इसका 0.2 वोल्ट है। ऑल राइट, सो आई होप दीज रीजनिंग्स आर ऑल राइट एंड यू हैव अंडरस्टूड इट। Actually they will not ask you the reasonings and all, no one is going to ask you the reasoning, they will only ask that किसका थ्रेशोल्ड वोल्टेज कम है और किसका ज्यादा है, और वो आपको तोते जैसा बाय हार्ट करना एक ऑप्शन है। नहीं तो अगर आप समझ के लोगे कि किसका ज्यादा क्यों है, then it's easy to remember that. Okay, so that is the reason why I gave this equation, because this equation will helps us to understand that why germanium का threshold voltage silicon से कम है। Fine. And I have also written here that the PN junction does not follow the Ohm's law, and it's a non-linear device. That is because of this exponential curve, what you see here. So we can go to the next slide now. So you can copy this down, and let's go ahead. So why we call the PN junction as a diode? We are writing it here. So as you can see in this VI characteristic, when the diode is forward biased, see, PN junction is generally used in this region, as I already told you before. It is not used in this region unless it is planned to be used as a voltage regulator. So you can see in this region, it's very obvious that when the PN junction is operated in the reverse bias junction, it offers a very high resistance. That is why the current is small. Na? Current is small means what? High resistance to the flow of current. And here exponentially growing current. That means a very low resistance when it is forward biased. Or I can say that an ideal diode, if you talk about, ideal diode. So what do you mean by diode? First of all, diode means any device which will allow current to freely flow in one direction. See here, free flow of current in one direction, and does not allow the current to flow in the other direction. देखो यहाँ पे current allowed नहीं है flow करना. इस प्रकार के डिवाइस को हम टेक्निकली हम डायोड कहते हैं, इसलिए पीएन जंक्शन को हम लोग ने नाम दिया है डायोड. ओके. And if you talk about an ideal diode means no current in the reverse direction. यहाँ पे तो माइक्रो एम्पियर में है, but ideal diode means a device which will not allow any current to flow in the reverse direction. But we can call the PN junction to be nearly an ideal diode because this current is of the order of microampere, which is very small anyway. So I hope that why it is called as a diode is clear, Abhishek. Why PN junction is called as a diode? Are you hearing me, Abhishek? Clear, okay. चलो यहाँ से, और ये भी मैंने यहाँ पे लिखा हुआ है कि जो जनरल पर्पस डायोड है ये आप रिवर्स सैचुरेशन करंट के बियॉन्ड इसको यूज नहीं करते यहाँ पे, और इस करंट को हम लोग कहते हैं रिवर्स सैचुरेशन करंट. Okay, so this has so the drift current here is called as the reverse saturation current. So those points we are writing here. So previous slide. So this is your previous slide. So of course you have to take a reading of this chapter from HC Verma and CBSE book later on. You can read your textbook also, HSC book. Fine. ये वाला भी अगर आपने लिख लिया तो I can go ahead. So now we define the input resistance or the dynamic resistance of the diode. So dynamic resistance of the diode means if I vary the voltage, this voltage, then how much does the current vary? So change in the voltage delta V, how much does it reflect in terms of change in delta I? That is called as the dynamic resistance of the diode. And if you calculate this when the PN junction is forward biased, of course, even when it's reverse biased, you can calculate what is the dynamic resistance. Dynamic resistance is not for forward or reverse bias. It is for both of it. So in the forward bias situation, this dynamic resistance is going to be a small value or a very large value. What do you feel it's going to be? A small change in the input voltage in this region is leading to a very large change in the current, isn't it? So if delta V is small, then delta I is very large. Why? Because it is an exponential graph. We saw those equations. So therefore your RD is going to be very small. So in the forward bias state, I can say that your dynamic resistance takes on a very small value. How small? 10 ohms, 100 ohms, like that. And in the reverse bias situation, when your delta V is changing, your delta I remains constant. So if this remains constant, there is no change only happening here. So the dynamic resistance, when you're reverse biasing your diode, is going to be in mega ohm. Okay, or even more than that. Of course, I'm talking about this region where the diode is generally used in electronic devices. So we have to know what is the dynamic resistance. So dynamic resistance is defined as change in the applied voltage, forward or reverse, divided by the change in the current. And when the diode is forward biased, this dynamic resistance is in the order of few ohms. And when it is reverse biased, it is of the order of mega ohms. Okay, so now we will proceed from here, and we can maybe calculate this in this graph here. So this is the VI characteristic of the silicon diode. Calculate the resistance of the diode when the current to the diode is 15 milliampere here. Okay, and when VD is minus 10 volt. So one of them will give you a very small value. So you can check this out. You can say that the current is 15 milliampere, and when this current is 20 milliampere, at this point we are basically trying to find out the slope, because that value what we had defined, RD, that is delta V divided by delta I, is nothing else but the inverse of the slope out here. So you can take this value here, slightly above and slightly below you go. I'm interested at this point, so let me go slightly above and slightly below and say that, okay, at 20 milliampere, the value of the forward bias applied is 0.8 volt coming up here. And when the current is 10 milliampere, this value which I've circled here is approximately 0.7 volt. So your dynamic resistance, which is the change in voltage divided by change in current, will be zero point 0.8 minus 0.7 divided by your 10 milliampere, that is 20 minus 10. Okay, so that's going to give you a very small value, that is 10 ohms is your dynamic resistance in the forward bias condition. And in the reverse bias condition, at this value, you can say that, well, I can directly take, even if you change out, the value of current is almost constant here. So 10 divided by 1 microampere इस पॉइंट पे रिवर्स सैचुरेशन करंट आपका 1 माइक्रोएम्पियर है, तो दोनों को डिवाइड किया, यू कैन सी इट्स ग्रेटर देन 1 मेगा ओम, one order more than 1 mega ohm. So dynamic resistance is very high, and it's of the order of mega ohm when you are reverse biasing the diode, and it is very small when you are forward biasing the diode. So it's a small data related problem to confirm what are the values of the dynamic resistances. Going ahead from here, one small way, as I told you, to remember the symbol that this is an anode and cathode is that in German language, cathode को लिखते हैं cathode, ऐसा लिखते हैं वो लोग. तो ये जो K है, आप देख सकते हैं ये K जैसा दिख रहा है ना, ये K, ये वाला देखो K जैसा दिख रहा है, तो इस K को पलट दो, उल्टा कर दो, तो ऐसा दिखेगा. Okay, so this will just go on the other side. So cathode, make K is pointing towards the cathode. That's just a small way to remember कि कौन सा side anode है और कौन सा side cathode है. Okay, so you can see the symbol, flip it over, and wherever this side is pointing after flipping is basically your cathode. And if you pick up a PN junction diode, there is a marking on the PN junction diode, a silver marking, and this silver marking जिस साइड में रखा हुआ है वो ऐसे हम ड्रॉ करते हैं सिंबल को. ओके, तो यू फ्लिप इट ऑन द अदर साइड, तो कैथोड ये साइड हो गया, तो जिस साइड में सिल्वर लाइनिंग है वो साइड आपका कैथोड है. So when you fabricate a PN junction diode, it will look like this. I don't know how many of you all have seen a diode, but this is how it looks like. और यहाँ पे एक silver lining होता है, so that you can recognize which side is the cathode and which side is the anode, or which side is the P side and which side is the N side. Okay. Now, going ahead from here, actually from here we are starting as far as the HSC syllabus is concerned, because this parts, what was taught till now, you have studied in the 11th. Okay, so now we are going to start off with application of the junction diode as a rectifier. So what do you mean by rectifier? What does a rectifier do, and what is the application of that? If someone can throw some light on that. Shravan, uh, do you know what is a rectifier used for? Utkarsh, Varun. Okay, so my doubt, Utkarsh, is that a junction diode is used as a rectifier. So do you know what is a rectifier used for? What is the application of a rectifier? Inadvertently, we all use rectifiers in our day-to-day life. Okay, we are all using rectifiers in all the products which we have with us. But what is a rectifier? So some students are saying it converts AC to DC, and some students are saying DC to AC. अभी ये दोनों में से कौन सा करेक्ट है? दो दो स्टेटमेंट है. एक स्टेटमेंट है डीसी से एसी कन्वर्जन जो होता है वो रेक्टिफायर करता है, एंड सम पीपल आर सेइंग एसी टू डीसी कन्वर्ट करता है. तो इन दोनों में से कौन सा करेक्ट है? एटलीस्ट वो तो बोलो. Okay, okay. So they are correcting it. Sir, AC to DC hai. Okay. AC to DC conversion. Okay. So when we studied the topic of alternating circuits, you may be recollecting, we had stated there that what are the advantages of using an alternating current. For the transmission lines, we had discussed, many advantages. When you want to transmit voltages over long lines of more than miles and miles, if you want to do that with minimum amount of losses, then you have to use an AC current. That was the main conclusion, that why we needed alternating currents. See, all your devices, they need DC only. Like right now I'm using this laptop. This laptop doesn't require an AC current. It actually requires a DC current. So even if you're having an AC current which is generated and it is coming across the transmission lines, you need to convert that AC into DC. Otherwise, this device cannot operate at all, isn't it? So that's basically one of the functions of the rectifier. So you have the 230 volt coming over in your main supply. Before connecting it to the rectifier, there is one more device. What is that device which you have to use before the rectifier, just before the rectifier? Anyone can tell me what is the name of that device? यानी एसी पावर आ गया आपके घर में, तो उस एसी पावर को रेक्टिफायर को देने के पहले एक और डिवाइस लगेगा, इलेक्ट्रॉनिक डिवाइस. व्हाट्स दैट? Or I will say it's an electrical device rather than saying it's an electronic device. What is the name of that electrical device which you have studied in alternating circuits chapter? ये आपका clue है. Transformer. Yeah, transformer will be required because you'll have to step down the voltage before you connect to the rectifier. Otherwise, आपका rectifier उड़ जाएगा. You know that the PN junction, you cannot apply a very large voltage. बहुत ज्यादा वोल्टेज अप्लाई किया तो हीटिंग के कारण वो उड़ जाएगा. It will become heated and it will get burnt off. So first you have to bring down the voltage AC, and only then you can connect it to the rectifier. Okay, fine. So now let's see this one here. So we know that from the VI characteristics, we know that this diode is going to allow current only when it is forward biased. When it is reverse biased, it does not allow the current to flow. That is why it was called as a diode. And it is precisely this property that we are going to use when you are going to apply the diode as a rectifier. Okay, so if there is an alternating voltage which is applied across the diode, you can expect that current will flow, at the output of the rectifier only when the diode is forward biased. When the diode is reverse biased, so if you're having a AC supply like this, so in this region, only the diode will be forward biased. And in this region, the diode is going to be reverse biased. So therefore, you can see that this part can be cut off. Okay. So of course, rectifier does not directly convert into DC. There are many more stages which are there, and we will see some of those stages in our discussion today. That how do you convert an AC to DC? ऐसा नहीं है कि rectifier को connect किया तो direct DC हो गया. There are some more elements coming over. Okay, चलो. तो इस property को हम कहते हैं rectification of the alternating voltage, and hence इस यहाँ पे नाम आ गया rectifier. हम रेक्टिफाई कर रहे हैं ऑल्टरनेटिंग वोल्टेज को, उसको डीसी बनाने का कोशिश कर रहे हैं. इसका मतलब है हम रेक्टिफाई कर रहे हैं. ऑल राइट, कैन वी गो अहेड इन दिस थीम? रचना, so can you explain this graph again? I got disconnected. No, I'm going to explain the graph. I told that the junction diode is going to be used as a rectifier, and it is going to convert AC into DC. And these graphs we are going to explain in detail in the upcoming slides. So your basic rectifier, which is going to be called as a half wave rectifier. Of course, half wave rectifier is going to be of no complete use to us, but we are starting with a half wave rectifier, and then we will see how to form a full wave rectifier. We call this circuit as a half wave rectifier because given an AC supply, only half of this wave is converted into one side. Okay, बाकी पार्ट स्वाहा खा लिया सर्क्यूट ने. So इसलिए इसको हम हाफ वेव रेक्टिफायर कहते हैं. So you can see half wave rectifier consists of course ये रेक्टिफायर का पार्ट नहीं है, ये हमने ट्रांसफॉर्मर दिखाया है बिकॉज हमको पता रहना चाहिए कि डायरेक्टली एसी मेन सप्लाई आप डायोड को नहीं दे सकते, आपका डायोड उड़ जाएगा. So first you have to step down the voltage, and then when you have a stepped down voltage which is an input AC connected to this diode, यहाँ पे symbolically represent कर दिया है हमने डायोड को. We know that this is the P region and this is the N region, and through a load resistance. Okay, ये जो लोड रहेगा ये आपका कंप्यूटर हो सकता है लोड. Okay, ये लोड यानी फिजिकल रेजिस्टेंस नहीं होता है वो. That is a computer which requires a DC voltage. So you can see that during the positive half cycle, ये जो आपका P junction है यहाँ पे ये पॉजिटिव रहेगा, and therefore it will be forward biased. And forward biased condition, we know that you are going to have a current on the output. So your PN junction acts like a short circuit. It's a complete short circuit. There is a free flow of current, and that short circuit is what I am representing in terms of the voltage across the RL here. Okay, so current will flow through the load resistance, and the way the input voltage is going to vary, the current will also increase accordingly, and the voltage across the load will also increase accordingly, like this. That is why you get like this. And here you can see that this diode is going to be reverse biased. So here forward biased and here reverse biased. So if it is reverse biased, there is going to be no current, and if there is no current, then nothing is there here. Of course, there is going to be some reverse saturation current, but that's going to be in microampere. It's going to be very, very small. So approximately we show it as if it's zero only here. So this is called as a half wave rectifier. Is this all right? Varun Sharma, are you hearing? Are we understanding what has been taught? And are you hearing what I'm saying? Okay, so Varun is not hearing. Fine. Going ahead, certain things what I told in the last slide are put forward here, that why it's called as a half wave rectifier, so that you can just briefly take down before we go into the full wave rectifier. So full wave rectifier, you will have on both sides rectified voltage. So in order to get a full wave rectifier, what do you think we have to do now? What changes you think Shreya will have to do in here so that we can get a full wave rectified voltage? One small change you can say. What will you add in this circuit so that both the sides will be rectified? Mohit is saying introduce reverse biasing. Okay. So we will be adding two diodes. Okay. I think, but before that, what is written here? Can you explain again the half wave rectifier? Okay. So half wave rectifier mein, as I told you, that during the positive half cycle, that is this region, this diode is forward biased. So when it is forward biased, we know that the current flows. Na? Forward bias condition means your diode acts like what? Short circuit. That's how we model a diode. A diode is modeled as a short circuit when it is forward biased, and it is modeled as an open circuit when it is reverse biased. Open circuit means very less current flowing. So in the forward bias situation, the current will freely flow and you will have a drop here like this. And as the input voltage varies, the input current will also vary and the output voltage will also vary in the same fashion. So that is why we get a graph like this when you're, the positive cycle. And as far as the negative cycle is concerned, then this is minus and this is plus when negative cycle is happening. So अगर मैंने यहाँ पे नेगेटिव लिख दिया, ये तो पी एन और ये एन है, तो ये आपका जो पी एन जो है डायोड, ये रिवर्स बायस हो गया. और यहाँ पे मैं लिखूंगा फॉरवर्ड बायस, यहाँ पे लिखूंगा रिवर्स बायस. So when it is reverse bias, there is going to be no current, or we say microampere, which is very less. So that is why here there is no current. So if there is no current, there is no voltage drop across the load. So that is why it's flat, and this whole process keeps repeating. All right. Half wave rectifier. Now, going ahead here, yeah, one care you have to take, of course, is that this reverse biasing should not exceed the peak reverse voltage and ensure that the diode does not go into the breakdown region, because reverse direction mein, you need to take care of that. Otherwise, if the diode goes in the breakdown region, then it will no longer function like a normal diode. Very large current will start flowing through the diode. So that's one care we need to take care. Okay, going ahead, we will say that if you want to rectify both the sides, then we will have to use a full wave rectifier where both the sides have to be rectified. Okay, so right now we have only accomplished a half wave rectifier where only half of the input AC has been correctly rectified. But now, of course, if you want a DC value, you will require first both the negative and the positive half cycles properly. So the simplest rectifier what you could have is called as a center tapped. There are two types of full wave rectifiers, but we have in our syllabus only one of them. So one is called as a bridge wave rectifier, where the diodes, 4 diodes are used in the form of a bridge. The same way which we used in electrical circuits ke chapter mein, there was some bridges used there also. So same type of bridge wave rectifier is there, but we don't have that in our syllabus. So center tapped full wave rectifier. And this center tapped full wave rectifier, naturally we'll expect 2 diodes, because if we want to rectify both the cycles, then we will have to use two diodes. So you can see here that this is a step down transformer. It's called a center tap because you are taking a connection from the center of the transformer, and the two diodes are connected here. And this circuit could also be in a very simple way drawn like this resistance I can connect it like this also. It's the same thing. ऐसा कनेक्ट करो या ऐसा कनेक्ट करो, फर्क नहीं पड़ता. तो यहाँ पे देखो, मैं यहाँ पे लिखता हूँ साइंस. When I'm talking about the positive half cycle, then these are going to be the voltages, you know, the signs of the voltages which are going to be developed on the secondary side of the transformer. That is during the positive half cycle. So as per this diagram, you can see that the top diode is going to be forward biased. And you can see this sign, this diode is going to be reverse biased during this side. Okay, so that means that in the positive half cycle, this diode is going to conduct and the current will flow like this. It will come here like this. Okay, and if I show it in this diagram, it will look like this, come like this, and complete the circuit like this. So this is the entire circuit like this, complete. And when I talk about the reverse direction, okay, then now instead of writing like this, let me rub this. It will look like this. Negative, यहाँ पे positive, यहाँ पे negative, यहाँ पे positive, यहाँ पे negative. That means during the negative half cycle, this is going to be positive, negative, positive, negative. That means that this diode will become forward biased. And see, in both the cases, first case में भी current ऊपर से नीचे flow हुआ. देखो यहाँ से ऐसा जाके ऐसा नीचे flow हुआ. और इस केस में भी करंट ऐसा जाके नीचे ही फ्लो हो रहा है. तो दोनों केसेस में, यानी पॉजिटिव साइकिल हो या नेगेटिव साइकिल हो, द करंट फ्लोइंग टू द लोड रेजिस्टेंस इज इन द सेम डायरेक्शन, एंड देयरफॉर यू कैन सी दैट द करंट शोन इन द सेम डायरेक्शन यहां पे भी. ओके, सो दोनों के केस में नीचे करंट फ्लो हो रहा है. तो अगर नेगेटिव हाफ साइकिल है तो करंट कैसे फ्लो होगा? It's going to flow like this through this path, come like this, come like this, come here, and complete the circuit like this. So this is the way the current is going to flow in the negative half cycle. So what I've shown here is how the waveform at A looks like and how the waveform at B looks like at any point of time. They are out of phase. So during the positive half cycle, this one will ensure that the top diode is forward biased and you will have a rectified output. And during the negative half cycle, this voltage is positive applied to the diode too, and this side is also rectified. Okay, so how do I assign those signs? पॉजिटिव हाफ साइकिल हियर. सो पॉजिटिव हाफ साइकिल में मैं यहाँ पे पॉजिटिव लिख सकता हूं. ऊपर वाला जो पार्ट है ये पॉजिटिव रहेगा. ओके, और ये जो पार्ट रहेगा ये नेगेटिव होना चाहिए ना. ओके, ये वाला पॉजिटिव, ये वाला नेगेटिव होगा. तो दैट इज व्हाई हियर आई राइट हियर पॉजिटिव एंड हियर आई राइट नेगेटिव. ये हायर पोटेंशियल पे है कंपेयर टू द सेंटर ऑफ द ट्रांसफॉर्मर. This is the higher side of the transformer. This is the center of the transformer. The positive and negative sign shows that which side is at a higher potential. What do you mean by positive and negative? Positive and negative means which side is at a higher potential. तो इसका मतलब पॉजिटिव का मतलब है ये हायर पोटेंशियल पे है कंपेयर टू द सेंटर ऑफ द ट्रांसफॉर्मर. और ये पॉजिटिव का मतलब है कि ये जो पॉइंट है ये इस साइड से हायर पोटेंशियल में है. दैट इज द मीनिंग ऑफ दिस पॉजिटिव नेगेटिव पॉजिटिव नेगेटिव. ऑल राइट.